So welcome back to Calc 2. We're going to start chapter 11, where we're going to look at something called power series. So as I go through this chapter in the various videos, I'm going to skip around in the sections a bit. There are 4 sections. I will make sure I try to tell you exactly where we are. But for this one, we're just going to do a little bit of a broad overview. So to do that, we're going to start with a series that you've already worked with. And we're going to start with the geometric. So you know the basic geometric series. If I have the summation of, say, I don't know, n going from 0 to infinity of, let's just say 1/2 n, right? So what exactly does that look like? Well, this is a very basic geometric series. You start with 0. Well, 1/2 to the 0, of course, is 1. Then it's 1/2 to the first, 1/2 to the second, 1/2 to the third. Sorry, not 1/3. I don't know where I got that from. 1/2 to the third, and so on and so on and so on. Okay, so you understand this series. It's your basic geometric series. In fact, you even know that this series converges, right? Because our r equaling 1/2 is less than 1. You also know it's one of the only series we can determine what it actually converges to, right? We can sum this series, right? And we can say that the sum is a, meaning the first term, over 1 minus r. Our first term is 1. 1 minus r is 1/2, so that's another 1/2, and this is 2. So we know that the summation n equaling 0 to infinity of 1/2 to the n power equals 2. Oh, that's great. Now, again, so what are power series? And the other series that we're going to learn in this particular chapter are power, then a specific type of power series called a Taylor series, and then a specific type of both of those called the Maclaurin. So to get started, let's talk about what all a power series is, well, let me take my series, like this geometric here, instead of using a nice rational number like 1/2, that we could calculate the value of every single term, let's just simply replace it with x. Okay? So I said, we're going to start with a very, very basic series that you're kind of familiar with. So this x is some unknown value, all right? And this is what we would consider a very, very basic power series. And we'll define the actual power series in a little bit. But this would be considered, so what does this look like? Well, if I were to expand it, so we're going to look at expanding our power series of x to the n, x to the 0, you end up with x to the 0 plus x to the first plus x squared, and you get the idea. Now, real quick, I'm going to replace that x to the 0 with 1, right? And I'm not going to write. Oh, well, that's kind of familiar to us, isn't it? Wouldn't you consider that just a basic polynomial? Now, you're used to polynomials, of course, starting with the highest exponential term and then going down. In this case, we have to start with our lower term and go up because we really don't have an ending to our polynomial. So this is kind of like an infinite polynomial, right? That's all it is. It goes on and on. Now, here's the interesting thing. Let's just assume our x is less than 1 and we can actually get the sum of this. Because we can get the sum a converging geometric series. So let's just assume that Think about that. So that means my sum of let me redo that. 1 minus x, right? Hold on. Sorry. Because my first term of a in this new series is just 1. And my r equals x. So my sum would be 1 over 1 minus x. And then in theory, of course, assuming, yes, that x is less than 1, we could say that the summation of x to the n equals 1 over 1 minus x. Well, that's kind of interesting if you think about it, because this is a rational function, right? 1 over 1 minus x. And this we just showed to be basically an infinite polynomial. So in essence, the idea here for all of the stuff we're going to be doing in this chapter is we can take some more complicated rational function, right? And in fact, you're going to see shortly, not only in the next video, likely, not only rational functions, we could do trigonometric functions, we could do logarithmic functions, exponential functions, all these kind of more difficult functions, and rewrite them, possibly, as a polynomial. Infinite polynomial, but we can certainly estimate it. Well, this is a little bit hard to believe, so let's take a look at it on a graph. Again, it's just a broad introduction, so let's just get an idea of what's going on here. Let me go over to Desmos. And let's type in our function. One over 1 minus x. All right. And actually, I want to, hold on, just make that in black. There we go. All right. There's our simple function, 1 over 1 minus x. All right. So let's take a look at the polynomial we just kind of started to create when we expanded that. So remember, when we took the summation 0 to infinity of x to the n, what did that look like? Well, it started with just a 1. That was my first expansion. All right. We just can't put 1. Sorry about that. You have to put y equals 1. Okay, so our first expansion is just a horizontal line. That really doesn't help us in any way. What's the second? So we're going to call that first term the first term of the expansion. What's the second term of the expansion? Including the first, so that would give me 1 plus x. So here I want you to notice that where this is occurring, this 1 plus x, right? It's just a straight line. If you recall back to what we did in Calc 1, this blue line here, which is the 1 plus x, our second term expansion, happens to be the tangent line when x equals 0 of 1 over 1 minus x. Just pointing that out. Okay, what happens if we add a third term? I'm going to do it with another line. So now I'm going to have 1 plus x squared. Now, once we revert back to that color for me, let's make this one orange. Okay, now see the orange line. All right. Notice it too is hitting my graph at exactly at the x equals 0 point, just like our tangent line did, and just like basically our horizontal constant line did. But it's wrapping itself a little bit closer to our curve than our tangent line does, our quadratic. So let's look at a third term expansion. So that's doing 3 terms. X plus x squared plus x. Now I need cubed. So I can come in a little bit here, I believe. Doesn't want to let me. There we go. We can come in a little bit because clearly we don't care about the rest of the graph. We're looking at what's happening right around when x equals 0. All right. You can kind of see here the red line is wrapping itself just a little bit closer to that black line than even the quadratic did. So that was a cubic. Let's go to a quartic. So let's go to 1 plus x squared plus x cubed. Now we're going to add an x to the 4th. Again, try to get in here. Change the color. Keeps wanting to go back to the same colors for me. Hold on. Oops. Let's make this one green. I want to make sure they're all in different colors. All right. So that green line, you can kind of see right here, stays closer to our original black line a little bit further out than the other lines do. And of course, I hope you kind of get the idea of what's happening now if we were to take it a step further. So let's do it this way now. Let me do this. Let me get rid of the other lines. All right. And let's just keep adding on now. All right. So I can add on plus x to the 5th. Look at that. It's really wrapping itself around now. It's coming all the way out to almost to -1, +1. Plus x to the 6th. Going out even further. We'll just do one more. I think you're getting the idea. Plus x to the 7th. Yeah. And it's just going to keep starting to wrap itself a little further along the actual curve. So, what does that tell us? Let's go back to our function. So we can see that our polynomials, when we sum, all right, when we sum this, right around that 0 mark, starts to kind of estimate the rational function 1 over 1 minus x. So there's an interval where we could actually use maybe up to 6 terms or 4 terms of this expansion to estimate our rational function. That's where these series we're going to work with in this chapter become useful. And we're going to do quite a few more of them. But what is that? So let's actually define now our power series, because the one I gave you was it didn't have a coefficient. It was centered at 0. So by centered at 0, what I want you to realize, because you're going to see that a lot in these definitions, is that means that the estimate of the polynomial for this rational function is very close on an interval around 0. So that's what we mean by centered at 0. So let's put some general definitions. So the summation of n equaling 0 to infinity. Now what we didn't have is a coefficient of these this polynomial. So see, each of them just had a coefficient of 1. So we're going to add in a coefficient for our definition. We're going to call it some coefficient n, because the coefficient could be different for each term. So we don't know what those coefficients are right now of x to the n. So what does that look like? Well, the first term, the x is going to go away because that's going to become a 1. So you have our coefficient sub 0, coefficient sub 1 when x is to the first, coefficient sub 2 when x is squared, and coefficient sub 3 when x is cubed, and so on and so on and so on. This is a power series that is centered at 0. Okay? So now, what does the equation look like if your power series is not centered at 0? So that means that level of convergence where all of the polynomial expansion is matching the actual function is occurring somewhere else besides 0, like we saw in the example. Well, that's going to look like this. Still need your coefficient, but now you have some shift, right? And this is your, so what is that going to look like again? C sub 0, if you expand it out, C sub 1, x minus some value a, plus C sub 2, x minus a, and then that's squared, plus C sub 3, x minus a cubed, dot, dot, dot. And this is centered at a. And that's going to give you a left to right. So minus a. So if your a is actually a positive value, so if you have x minus 3, let's go back to our function for a minute. If this were x minus 3, then you'd have to come over here to where the 3 is, and it would actually be around this polynomial, this part of your graph, all right, if we're centered at 3. That's where the convergence of the functions would occur. All right, so x plus 3 would go to the left, of course, and the x minus 3 would go to the right. So these power series can look pretty much like anything. Let's take a look at a couple examples. Let's look at, so this is by the way your definition of basic power series, and we're going to streamline or make that a little more specific in a minute. So let's look at an example. How would I expand? Oh, I don't know. Let's do summation 0 to infinity of n x to the 2n. So that would be pretty easy. Just plug in your 0. The whole first term goes away. There is no, it becomes 0, right? And then when n is 1. And here's what you want to be careful when you're expanding these. It's not the x value you're plugging the values into. It's the n. This is n equaling 0. So when n is 1, we get x squared. When n is 2, I get 2x to the 4th, 3x to the 6th, dot, dot, dot. And there's different ones that you can look at. Let's do, what if it were a factorial, right? N equaling 0 to infinity, n factorial, x to the n. These are still centered at 0. So first term is, don't forget, what is 0 factorial? Do you remember what 0 factorial is? That equals 1. If you don't know that, that's an important little piece of information. So that's going to give me 1 plus When x equals 1, I get 1, x to the n, so that's just x. X equals 2. 2 times 1 is 2. 3. 3 times 2 times 1 is 6. 4 times 3 times 2 times 1 is 24. Dot, dot, dot. And you'll start to kind of, we're going to be doing one, we're going to be using these factorials a lot. So you'll get the idea that it's 1, 2, 6, 24, 120, so on. And let's look at one more. Summation 1 to infinity n plus 1 x minus 2 to the n. So this one we're going to start at 1. 1 plus 1, that's 2. X minus 2 to the first. So 2, 2 plus 1 is 3. X minus 2 to the squared. 4x minus 2 to the third. Dot, dot, dot. So this is just to practice, you know, expanding out some of these power series. But with these particular series, you know, they're not easy. They're not like a basic geometric where I know what it summed to. All right. I knew the formula for what the geometric sum to. So that was why we did that one first. This is just practicing expanding them out. Now, wouldn't it be great, though, if I could start with a more complex function? When I say complex, we're not talking too complex. We'll start with things like sine of x and cosine of x and e to the x and stuff like that. And I can use that to build a polynomial function around that. We can do that, but we need to define our c to the end. So if we let our c to the n of our basic power series, this c to the n value, we need to come up with a formula for that. And if we come up with a formula using derivatives, so we're going to call this, so f to the n meaning when n is 1, you have the first derivative. When n is 2, you have the second derivative. When n is 3, you have the third derivative. So each coefficient is going to be based on the derivative of a, whatever we're centering it around, divided by n factorial. And you're thinking, where's this n factorial coming from? Well, I want you to think for a minute, because if I take a first derivative and then a second derivative and a third derivative, remember, you're constantly multiplying by the next exponent. So this is kind of where your factorial comes from. And this is all going to be computed at a, wherever you're centered. So again, you're thinking, why am I writing c to the n from my power series equaling this? So let's just take a look for a second. Don't forget your original power series is simply 0 to infinity of c to the n x minus a to the n, right? So if I let that be the function, because remember, we're looking at this as if I expand it out, it's going to be a polynomial, so I'm going to let it equal f of x. So you have c to the 0, we've already done this above, x minus a plus c2, x minus a squared plus c3, x minus a cubed, and we're just going to go up to c4. You know, and maybe you're not interested, you're just accepting the fact that I'm going to call that the coefficient, but if you want to know where kind of it came from, we'll just do this a bit quickly. So what I want you to do is just start taking derivatives, right? So f prime of x, the first coefficient is going to go away. C sub 0 goes away, right? What's the derivative of this? Well, the x term's going to go away, right? Because C1 times x, C1 minus a, that's going to be a coefficient. That's going to go away. So you're going to just have C to the 1, right? C sub 1. That's it. Plus, oh, what's the next term going to look like? The 2 is going to move out front. So you have 2 C sub 2 x minus a to the first power times the derivative of x using chain rule. That's it. All right, so we're going to do these derivatives quickly. Then you're going to have 3c sub 2 x minus a. It's going to go down to the squared, and then the chain rule just times 1, and 4c to the 4 x minus a. Cubed. All right, I'm going to do another derivative. Just bear with me. All right, first term, c sub 1, goes away. The second term, all I have is 2c sub 2. Okay, plus, now the third term, that's the tricky one here. I'm going to move the 2 out front, so I'm not going to multiply them together. I'm going to write it as, I'm going to have my 3 that's there times the 2 times C2. Now I have x minus a to the first. All right, plus, what's going to happen on the next one? It's going to be 4 times 3c to the 4th x minus a squared, dot, dot, dot. Okay, we're almost there. So if I do it a third time, and again, you don't need to do this. This is just trying to show you why something is what it is. 2 to the c squared is a constant. That goes away. X minus a, well, we need the coefficient because that's the first power, goes down to 0. That goes away. So I'm left with 3 times 2 times c squared. What's my next term? To move the 2 out front, so then I have my 4 times 3 that's there, because again, now this is the first one I got to be concerned about. 4 times 3 is there. Now I multiply it by the coefficient, the exponent that I moved out front, c to the 4th x minus 1 to the first, dot, dot, dot. We're going to do just one more. Now, you notice how we do Roman numerals 1, 2, 3. Once you get past that, you just call it f to the 4th in parentheses. All right? Of x. Coefficient goes away. What am I left with? This one goes away. So I have 4 times 3 times 2 times 1 times c to the 4th. Plus dot, 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 dot. We don't need to continue it. So here's the idea. We're going to center it at a. That means I need f of a for each of these. Well, if I make my x equal a, all these other terms are going to just go away, right? A minus a is 0, a minus a is 0, a minus a is 0, 0. Everything goes away. And what am I left with? Okay, well, there's a pattern here. Look at this pattern for a minute. I have f to some derivative of x, 4 times 3 times 2, 3 times 2, 2 times 1, 1. Whatever that derivative's factorial, c to that derivative subscript. So that would mean my c to the n is going to equal f to the n of x divided by n factorial. So that's kind of where it comes from. You think, well, why do we keep taking these derivatives? Well, remember, the whole goal is we're using that tangent line and expanding it and wrapping it around our functions. That's what we want to do. We want to come up with these polynomials that can wrap around our functions. And the derivatives, the slope, getting those slopes can help us do that. So what is this that we just came up with? This is called a Taylor series, or a Taylor, when it's written out in polynomial form, a Taylor polynomial. You will, when you get to differential equations, you'll spend like an entire chapter on these things. these Taylor polynomials, it is a specific type of power series where we define the coefficient. So what does it look like? The f of x, that's our function, is going to be this summation 0 to infinity. My coefficient is now f, use the parentheses with the number in it, of a over n factorial, because remember, we want to center everything at a, so it becomes a, of x minus a to the n. Okay, this looks like, then, when you expand it out, let's see what our Taylor series expanded out, which then becomes our Taylor polynomial, looks like. In fact, I'm going to do this, not that it matters. I'll just put the series there and then the polynomial down here. So what does that look like? Well, okay, what happens when n is 0? Well, that means I'm not taking a derivative, so I just have f of a. N factorial becomes 1, and that to the 0 is 1. So we just have f of a. All right, plus. Now first is f first derivative of a over o. Just 1 factorial, so we don't need that. I can get rid of that fraction bar. And that's just times x minus a. All right, so f second derivative of a over 2 factorial. I'll put the factorial in, but of course 2 factorial is just 2. X minus a squared. We'll take a look at one more. Plus f third derivative of a over 3 factorial of x minus a cubed. And this goes on and on. This is your Taylor series and Taylor polynomial. This can be used to estimate almost any function. Couple cool things about this. You might recognize this piece of it. The first two terms of an expanded Taylor polynomial is just your linear tangent line at A. Look at that. That is your linear tangent line at A. So if you have an f of x function, this represents the line that's tangent to that function at A. We worked with this in Calc 1. We did linear approximations. All right. So your linear approximation was simply your first two terms of your Taylor series. But remember, when we did linear approximation, here we had some function f of x. There was the first two terms. Guess what's going to happen as we add more expanded terms? Your function is going to start to wrap around with each increasing term. Your function is going to match, your polynomial expansion is going to start to match your function. And that's kind of what we're going to get into in the next video. So I said we're going to do 3 series. So far we looked at the power series. We saw what a power series looks like when expanded centered at 0. We saw the equation centered at A. So we can do the same for the Taylor series. And in fact, if you center your Taylor series also, if you center it at 0, well, how is that going to change my series? So centered at 0, we would just have the summation n equaling 0 to infinity. Then we have f to the n of 0. So we know what a is if we're centering it at 0. N factorial, and then just x to the n because you don't have the x minus a because it's 0. And you can kind of get an idea of what this one's going to look like. It's just going to start with just f of 0, whatever f of 0 is, whatever your function is, plus f first derivative at 0 times x to the first plus second derivative at 0. Now we got to put it 2 factorial and then x squared, and then the third derivative at 0, right? 3 factorial x cubed dot dot dot. Okay, this is called a Maclaurin series. So it's simply your Taylor series centered at 0. Why do we center it at 0? It's just easier to work with. And what that means, what you're going to see in the next video is, so in the next video, we're going to do some practice problems, and we're going to take a couple functions like sine and x, and we're going to turn them into polynomials.